Hi, my name is Veronica Qinglu, and today I'm going to talk about our paper, Faithful Chain of Thought Reasoning. This is joint work with Shreya, Adam, Harry, Deleb, Eric, Mariana, and Chris from the University of Pennsylvania. Let's start with the motivation. We know that chain of thought prompting is a very effective in-context learning technique for reasoning tasks. Instead of standard prompting, where the model only generates the final answer, CoT prompting additionally prompts the model to generate a reasoning chain before the final answer. And this has been shown to remarkably boost language models' performance on many complex reasoning tasks like math and multi-hop QA. However, if we consider the question, do CoT reasoning chains actually provide good explanations of how the model reaches the answer? Probably it's not that obvious. Take a look at this example. The input is a math question, but you don't have to read it. You only need to look at the output from chain of thought prompting on the right. And you'll notice that the answer in green is not even mentioned in the reasoning chain in blue. This is an example of how the answer does not always follow from the reasoning chain. And that means chain of thought prompting does not necessarily provide a faithful explanation, where faithfulness means that an explanation should accurately reflect how the model arrives at its final prediction. In other words, the language model does not always say what it thinks when predicting the answer. Why is the lack of faithfulness a bad thing? Well, there are several risks, and an unfaithful explanation can give the audience a false impression of the model being self-interpretable. And also it can induce the user's overtrust in the model more easily, which is especially dangerous in high-stakes domains like law and healthcare. In light of this issue, in this work, we come up with an approach to bridge this faithfulness gap. And our approach is called Faithful Chain of Thought Reasoning. Specifically, we decompose the reasoning task into two stages, translation and problem solving. In the translation stage, given a natural language query, a language model called the translator would generate a reasoning chain, which interleaves natural language and symbolic language. In the natural language part is a decomposition of the original question into multiple simpler sub-problems, and the symbolic language part would address each sub-problem. And then, in the problem-solving stage, a deterministic solver executes the reasoning chain to derive the answer. For example, if the query is a math word problem, Codex, the translator, would generate a reasoning chain consisting of natural language sub-questions as well as Python programs to solve each sub-question. Then, this reasoning chain is executed by a Python interpreter to derive the answer. And this process is faithful by construction because the answer is now the result of deterministically executing the reasoning chain. So the chain has to accurately reflect how the answer is arrived at, which is the definition of faithfulness. And this approach can be applied to a variety of reasoning problems when integrated with different choices of symbolic language and the solver. Next, we'll show a couple of examples. The first example is math reasoning. And here's a math question from the GSMAK dataset. If there are 3 trees in a parking lot and 2 more arrive, how many cars are there in total? The LM translator would generate a reasoning chain consisting of 3 simpler subproblems and a piece of Python program to address each of them. Then, this reasoning chain is fed to a Python interpreter to derive the answer, 5. The second task is multi-hop question answering. For a question like, would an apple sink in water from the strategy QA dataset, we still decompose it into multiple simpler sub-questions like, what's the density of an apple, what's the density of water? But for this domain, the symbolic language is chosen to be Datalog, a declarative logic programming language. Each sub-question is answered in Datalog, and this entire chain is fed to a Datalog interpreter to deterministically derive the answer, no. All right, the third task is relational inference. Here's an example from the Clutter dataset, which contains short stories involving family relationships between people. For example, Gabrielle drove her daughter Dorothy to the hospital, and Dorothy's son Vincent showed up shortly after. Then the question asks, how is Vincent related to Gabrielle? To answer this kind of question, we still decompose it into multiple simpler sub-questions in natural language. But now, the symbolic language is custom-defined logical expressions. For example, the first blue expression means that Vincent is Dorothy's son. This chain is fed to a rule-based inference engine, which iteratively derives a relationship between the target entities, Vincent and Gabrielle, using a series of rules, like one's daughter's son is one's grandson. Finally, we have the planning task. And here is an example from the SayCan dataset, where a user interacts with a robot in a kitchen scenario. The user would give out queries like, I spilled my Coke on the table, could you throw it away and bring something to clean it? The task is to derive a plan consisting of a sequence of actions the robot can execute to achieve this query. To solve this task, the language model translator would decompose the user query into a goal consisting of multiple sub-goals like throw away the Coke and bring a cleaning tool. Then it expresses the goal in PDDL, or Planning Domain Definition Language. This goal is fed to a PDDL planner afterwards, along with the necessary specification files of the scenario. Finally, the planner will deterministically search for and output a plan. Alright, now that we know how the method works, let's take a look at the experiments. We compare our approach to several baselines, including standard prompting that only generates the answer, chain of thought prompting, which additionally generates a natural language reasoning chain, and also leads to most prompting, which also decomposes the original question into sub-questions in natural language, but does not involve symbolic language, so still does not guarantee faithfulness. In our experiments, we use accuracy of the final answer as the main evaluation metric. We experiment with a couple of language models from OpenAI, including GPT-3, Codex, ChatGPT, and GPT-4. We evaluate on 10 datasets from 4 diverse domains: math word problem, multi-hop QA, planning, and relational inference. For all the baselines, we control the number of shots to be the same, from 6 to 10 following previous work. And we also experiment with 2 decoding strategies, greedy and self-consistency decoding. Now let's look at the results. First, we find that Faithful chain of thought outperforms all of the baselines on 8 out of the 10 datasets with the same underlying language model, here Codex as an example, and decoding strategy. Specifically, our approach beats chain of thought with an average accuracy gain of 5% on math word problems and 2% on planning, and 4% on multi-hop question answering, and a surprising 18% on relational inference. Since the release of ChatGPT and GPT-4, we also experimented with these latest models and got the new few-shot soda performance on 7 out of the 10 datasets. This suggests that we can actually improve the interpretability without sacrificing performance. Next, we also did some analysis on the robustness of our approach. In a nutshell, we showed that Faithful chain of thought is robust to the choice of exemplars as well as the phrasing of the prompt. Finally, we did an ablation analysis on the contribution of different components in the pipeline. Notably, one important part we find in this process is the solver. If we ablate out the solver, meaning that we no longer have the solver execute the reasoning chain, but let the model generate the answer by sort of internally executing the reasoning chain in itself, then the performance seriously drops in almost all cases. That means the role of the solver is not only essential to interpretability, but also to the performance. We recommend that you see more analysis and results, including the human evaluation, effect of language models and constraints, as well as error analysis in our paper. In conclusion, in this work, we propose Faithful Chain of Thought, a two-stage reasoning framework consisting of translation and problem solving. This guarantees that the reasoning chain provides a faithful explanation of how the model arrives at the answer. We evaluate our approach on 4 different reasoning problems and show that it outperforms existing baselines on 8 out of the 10 datasets, while additionally providing a faithful model explanation of the final answer. This shows a strong synergy between interpretability and performance. Finally, through a comprehensive analysis, we show the robustness of our method, the pivotal role of the solver, and also some frequent error patterns where it still struggles. Thank you for listening, and please feel free to check out our paper and repository.